Hi ladies and gentlemen, I'd like to welcome you to the third installment of the Private Pilot Ground School. I'm Kieno Thomas, your instructor. Again, any comments, questions, or concerns, you can email me at kienothomas@gmail.com. In the subject box, please put aviation so I know it's aviation related. So I do a lot of math and engineering subjects as well. Just to jump right in, I have a little bit of a stuffy nose, sore throat thing going on, so just bear with me a little bit. I might be gulping down water as I flow through the lecture, and I'm getting my first gulp in now. Okay. Get the pipes, get the vocals all lubricated and stuff. Alright, so first off, we are going to talk about aircraft instruments today. Okay. We're going to talk about the basic 6 flight instruments and how they work. What we have here is a aircraft panel. We have our radios and navigation stuff going on here, but our basic 6 flight instruments give us pretty much our primary flight information of what's going on with the airplane. We have an airspeed indicator, attitude indicator here, altimeter, vertical speed indicator, heading indicator, and turn coordinator. And what we're going to discuss or talk about is how they work today. So here's a little zoom in, little face-to-face view with these things, and our airspeed indicator actually tells us how fast we're going. This aircraft is moving about 130 knots, just a hair off. We're in a right turn, not really climbing, maybe a little bit, but we're definitely in a right turn, a little bit past 10 degrees. Our altimeter is almost at 3,000 feet. Here we have a right turn, coordinated right turn, because the ball is centered and the inclinometer. We have a heading indicator, and in this indication, it would be kind of rotating to the left, indicating a right turn. And then we have a vertical speed indicator. So these are our basic 6 flight instruments. Now, our basic flight instruments can be grouped in certain ways according to how they operate. We have vacuum-driven gyroscopic, and this is the label I came up with just to kind of define what they do, but these are vacuum-driven instruments. A vacuum drives these things, and there's gyroscopes in there. So the vacuum maintains the gyroscope, and there's a suction gauge that should be in the green to let you know that the vacuum system is operating properly. We have Pitot static instruments. The Pitot static instruments are driven by a Pitot tube and a static port. This is driven by a Pitot tube and a static port, static port, static port. But all 3 of these are a part of the Pitot static system. Then finally, we have what I would like to term an electrically driven gyroscopic instrument. And this instrument, DC electric, direct current electric. So these 2 are actually gyroscopic instruments, but for redundancy, we have something else to kind of help us out. And if this is level and then this attitude indicator was acting retarded, it would be like, hey, these guys aren't jiving. And then we follow up with other instruments to investigate if there's a problem with the system. So the systems are separated, and you may not always have a turn coordinator. Sometimes you may have a turn and slip indicator, but it's these 2 the turn coordinator and the turn and slip indicator give us the same information. The gyros inside of them, because again these are electrically driven gyroscopic instruments, are just kind of positioned differently, and they kind of sense different things. So, just to jump in. Vacuum-driven gyroscopic instruments. Alright. I don't know if you know anything about a gyroscope, but I'm just going to jump here real quick, and I'm just going to show. Now, the gyro's in the middle, and it's spinning. It's a heavily weighted rim. It's a metallic, object with a heavily weighted rim, and it's spun. And these gimbals would be mounted to the airplane, and the rigidity and space principle takes effect, even though it's just moving all around, right? The gyro's staying in its plane, it's staying in its lane. Like they say, stay in your lane. It's kind of staying in its lane, it's doing its own thing, and it's not letting the movement of the gimbals affect its movement. It's stabilizing. So this would kind of be like a artificial horizon. We move around, we bank the airplane, and this is mimicking what the horizon is doing. Okay, so just to jump back, with our vacuum-driven gyroscopic instruments, there are gyroscopes inside these two instruments, the heading indicator and the attitude indicator. Again, we have a suction gauge, and there needs to be an acceptable reading from the suction gauge to let you know that the vacuum pump is running. Now let's talk about how the air flows through the system. Okay, the air is vented from inside the cockpit, but there's a filter here, and this is why you shouldn't smoke in airplanes, because the smoke can actually clog the filter up, so you won't get as much use out of it. So you don't want to be smoking in the airplanes. Although if this is your personal airplane, you could, but you know, if you're renting aircraft and stuff like that, everybody doesn't like smoke, so be mindful of that. I didn't mean to go off on a tangent there, but I did. So air comes through the vacuum air filter. Air is pulled in here, the heading indicator, and air is actually sucked through the case. As the air is sucked through the case, the gyro is stabilized using its rigidity in space principle, and then it comes through a vacuum relief valve just in case pressure builds up somewhere, so the system doesn't hurt itself and the pump doesn't hurt itself, and then it's dumped out over an overboard vent line. Same thing with the attitude indicator. Sucked through the vacuum air filter, air is, I sound like Yoda on that one, right? The gyro inside the attitude indicator stabilized through the vacuum relief valve, through the vacuum pump, dumped out the overboard line. Okay. Sounds simple, right? Well, not so simple, but we'll come on down here. This is the attitude indicator. We have our miniature airplane, the artificial horizon, the sky and the ground. We're looking at the face of it. And again, the rigidity in space principle. The air is sucked past through the instrument. It spins the gyro up. Now these gimbals are mounted and they rotate so the airplane can bank and stuff like that. And the aircraft actually moves around this gyro as it's spun up. So you can read the little sidebar materials and stuff like that, but air is sucked through the case like I showed you in the diagram. Here's a little bit of a little movie I thought was pretty cool, a little video clip, and just hang out and watch it for a minute.
The attitude indicator shows an aircraft's position relative to the real horizon. The arc along the top, called the bank index, shows how far the wings are tilted. It has marks at 10, 20, 30, 60, and 90 degrees of bank. Lines above and below the horizon line show the pitch attitude of your airplane.
Okay, so I thought that was pretty cool. A pretty cool video.
The attitude...
It's trying to start up again on me. Now, back to our heading indicator. Same thing. Air sucked through the instrument case, through a relief valve, through a vacuum pump, and overboard vent line. Now, it's really important that you understand how these things work, because you know what happened with me was I just, my private pilot, instrument, commercial, I just learned what I had to learn. I really didn't bother myself with this stuff. I just knew how it worked and how it operated, but I really didn't understand the internal mechanisms. Now, you go down the road when you want to be a flight instructor, you're going to have to go back into this stuff. So it's just awesome. This is why I give the information now, because I just thought it sucked. Like, I didn't know how the inner workings of an attitude indicator worked. I just knew I had to have vacuum pressure from suction, and boom, it just worked. But the rigidity in space principles I really wasn't that thorough on, and the precession I wasn't as thorough on as well. What you need to understand about the heading indicator, it's a vertically mounted gyro. Again, air sucked through the case, spins a gyro, and this thing resists movement. so you get a good heading. The thing is if we look at gyroscopic precession, what happens is about every hour, probably about 15 degrees, you're going to lose, which means this card's going to slide. As force is applied to this gyro, it's just going to slide a little bit, and it just needs to be adjusted. What do we use to adjust it against? We use a magnetic compass. All right. So here's a magnet. This is what the face of the instrument might look like. Okay, but every hour or so, every 15 minutes, you really should be looking at this. When you're in level flight, you should be looking at your magnetic compass over here and using the adjustment knob to turn it. So let's just say if this was off, I have 240 on the lubber line, Lubber, and I would just rotate this thing until the 24 came to the top. Now, you really wouldn't be that far off, but I'm just saying, I'm just giving an example. When you look at the magnetic compass, hey, he says 240. Hey, I'm looking at 100 degrees. You would just rotate this until what's indicated on the magnetic compass is up top. And then you're good for another 15 minutes, and just periodically check it. Now, this little guy has errors associated with it, and we're going to talk about that. Okay, so our magnetic compass. Basically, there are short and long graduated marks. Alright, the short and long marks. The short marks represent 5 degrees and long marks represent 10 degrees. There could be a compass card on the pedestal mount type magnetic compass situation. What we need to understand is that geographically, you could never get to true north just following your magnetic compass, because this is a magnetic north directional seeking instrument. What that means is it's always looking for, or aligning itself, or comparing itself to where it is in relation to magnetic north. So you can never get to true north. If you look here at this slide, magnetic north is here, true north is there, and they're around 1,300 miles away from each other. Now, in order to get to true north, you would have to compensate for that error, because your compass is trying to take you there and you're trying to get here to true north. In that type of situation, we have to take in mind the lines of magnetic variation, which are here. All over the planet, you have what we call isogonic lines, which are lines of equal magnetic variation. So if we're flying around here, let's say in the Chicago area, I'm trying to think, Pennsylvania, Detroit, let's just say this is Chicago. There's no variation, so you wouldn't have to worry about that at this point. But if you're out like in California, we have to actually subtract 20 degrees from our magnetic heading in order to get to true north. So, you know, these are just lines of equal variation that we would just look at. Deviation. Deviation is basically, it happens because we have electrical instruments in here. Now this thing is looking for magnetic north, and then we're throwing more electrical energy to throw it off. So what happens is we have a situation where we're going to use a compass card. It's very small here, you can't see it. Here's a bigger compass card, or a bigger example of a compass card. And then if we were flying if we wanted to fly 090 with the radios on, we would actually have to fly 095 degrees, 5 degrees off. The magnets kind of align themselves with any magnetic field, or it distorts them or messes with them. So local magnetic fields in the aircraft caused by electrical current flowing in the structure and nearby wiring, or any magnetized part of the structure, conflict with the Earth's magnetic field and cause a compass error called deviation. So that's a problem, but we have a correction for it. Magnetic dip. as we fly over the equator, there's no magnetic dip. It's really nothing to worry about. But as close as we get into the northern hemisphere, the further we get to the poles, the compass card will actually try to dip itself. And I'm going to come up with a better, I need to get an inner diagram of actual magnetic compass so you can actually see it, but the bars inside the magnetic compass actually try to dip and align itself with the magnetic flux lines of the Earth. So there's a little friction that's caused, a little error that's called, and we have what we call northerly turning error and acceleration error. Just to go into that real quick, northerly turning error. Alright. Let's say we're on a northbound heading, and I got to get a better graphic for this, and I'm going to update this, but let's say we're on a northbound heading. To the right of me is east, and to the left of me is west. Alright, northerly turning error. Due to that magnetic dip, what's going to happen is, and just visualize as I talk to you, my nose is pointed north, on my right is eastbound, on my left is westbound. If I try to make a turn to the east, meaning a right turn, the compass is actually going to indicate a turn to the left, west a little bit. It's going to lag. Conversely, I'm on the northbound heading, and I'm going to execute a left turn to the west. I'm going to execute, the left turn, but the compass is going to indicate a turn to the east. It's going to lag. And it's going to gradually catch up at some point. So that's lagging. On the southbound heading, now imagine yourself pointed south. On my right, I'm southbound now, is west. On my right wing, on my left wing is east. If I could make a right turn towards the west, the compass is going to indicate a turn to the right, but it's actually going to look faster than what is actually occurring. Conversely, I'm southbound, I'm going to turn left. It's going to indicate a left turn, but at a faster rate than is actually occurring. So that is compass lag in the north, lead in the south. I'm going to come up with better graphics for this, because it's very, very important that you understand this, especially when you get into your instrument training. This is just a private pilot level, and there's really not going to be a whole hell of a lot of emphasis placed on this, but it's something that you're going to have to get. The next, for our purposes, private pilot purposes, acceleration deceleration error. As I accelerate, the compass is going to want to turn to the north. As I decelerate, it's going to want to come to the south, or turn south. And the memory aid is ANDS, A-N-D-S. Accelerate north. When I bump the throttle, the compass is going to want to turn to the north, decelerate south. As I pull the power back, the compass is going to want to turn to the south. So accelerate north, decelerate south. Our next group of instruments we're going to talk about are called the Pitot static instruments. They are driven, or let's identify them first: the airspeed indicator, the altimeter, and a vertical speed indicator. And these three instruments is the airspeed, vertical speed, and altimeter. They're driven by the pitot tube and the static port. Here on the wing we can see a pitot tube, and here we can see a static port. Now, this thing could be frozen over, iced over. We have a pitot heat switch to warm it up. And this thing could be covered in ice. And we have an alternate static air source. So there's some redundancy there, and redundancy is a big word, but all it means is it's backup. It's just backup. So we do that for redundancy, for backup. In case something happens here, with the pitot tube, we can warm it up. If this is iced over, we have an alternate static air source. Airspeed indicator up close, altimeter up close, vertical speed indicator up close. Now, how does this work? We looked at our pitot tube. We have ram air that comes in, and it's directly comes into not the instrument case, but the diaphragm, and it expands and contracts. The static airline just maintains atmosphere inside the instrument here for this diaphragm to expand and contract against. And as it expands and contracts, then there's some gears, multiplying gears there, and actually gives us an airspeed indication. So we see indicated airspeed, because there's going to be some terminology on this later. The altimeter, similarly, does not get any information like this instrument from ram air, but just a static line. So as the static port comes in, it feeds the outside, or the instrument case. Now you have what we call aneroid wafers, and these things are sealed up at a sea level pressure of 2992, which is our standard atmosphere. 2992 inches of mercury, 15 degrees Celsius, 59 degrees Fahrenheit. We have all these numbers. And in a perfect atmosphere, we should lose an inch of mercury per 1,000 feet. We won't get into the temperatures and stuff like that, but we'll talk about the inches of mercury, because this is what this thing is sealed up according to. And as the static port adjusts to the outside air, these things expand and contract, connected to some multiplying gears, and we get a altimeter indication. Now there's a couple other devices on this thing that we're going to talk about, but before I go there, we're going to talk about pressure. If we go from a high pressure area to a lower pressure area, from high to low, look out below, from low to high, look out sky. Which means when we go from a higher pressure area to a lower pressure area, our altimeter is going to actually make us think that we're higher than what we really are, and we need to be adjusting what we call a Colesman window right here. You would talk to air traffic control, you call flight service to find out what the current barometric pressure setting is, so you can properly set your altimeter in that case. So from high to low, look out below, from low to high, look out sky. Going from the lower pressure area to a higher pressure area, the altimeter is going to make you think that you are lower than what you really are. So again, a pressure adjustment has to be made in the Colesman window, and there's an adjustment knob and all that great stuff. Conversely, with temperature, same thing. The effects of non-standard temperature. I could be flying in an area where it's 30 degrees, flying to an area where it's 0 degrees Celsius, and I'm thinking I'm at the same altitude, but I'm actually getting lower. So from high to low, look out below. From low to high, look out sky. Same thing, non-standard pressure, non-standard temperature. So, those are the things or errors that can occur with our altimeter. Then we have our vertical speed indicator, sometimes called a vertical velocity indicator. What's going on with this is you have it very similar like the altimeter sealed wafer. Alright. No, it's not sealed. My apologies. We have a static line that comes right in here, right? And that static port feeds the inside of this diaphragm. Okay, so it's not ram air, it's not blowing it up and reducing it, it's just saying, hey, look, this is the outside pressure. Now, inside here, there's going to be a different pressure, but it's going to be letting pressure in and out, and there's a calibrated leak, which means there's a hole or an orifice, which is basically just a hole, and the instrument basically takes the pressure differences between the diaphragm and it trends the calibrated leak, and we get a vertical speed indication in hundreds of feet per minute. So this is a 500 foot per minute descent, 1,000 foot per minute descent, 1,500 foot per minute descent, 500 feet per minute climb, 1,000 foot per minute climb, 1,500 feet a minute climb, and then Cessna's probably not going to be doing a 2,000 feet per minute climb, but that's the climb, and that's the 2,000 foot per minute descent. Alright, so that is our vertical speed indicator and how it works. Couple things we need to talk about. We'll come back to airspeed because we have to talk about some definitions. Indicated airspeed. Indicated airspeed is the direct instrument reading obtained from the airspeed indicator. It's what you're looking at is what you see. No big deal. Calibrated airspeed is indicated airspeed corrected for instrument and installation error. Alright. There are many type of different flight attitudes where you will not get the correct indicated airspeed. So you can't. So there's a calibration to help you with that, to make the adjustment because of the plumbing and associated things of installing the thing in the position and stuff like that. There's going to be some errors associated with it. Not major errors, but we just want you to know it's an instrument, and in instrumentation we want to try to be as accurate as possible. The next airspeed we're going to talk about is equivalent airspeed. Equivalent airspeed really deals with high performance aircraft. Equivalent airspeed deals with high performance aircraft that move above, fly faster than 200 knots, and go higher than 20,000 feet. Not your typical training aircraft, but it's something that you need to be aware of because it's calibrated airspeed corrected for adiabatic compressible flow at a particular altitude. Compressibility, air just bunching up in front of the airspeed indicator or Pitot tube, ram air. As we get speeds above 200 knots or miles per hour, because air kind of bunches up in front of the airplane and it gives us abnormally high readings, airspeed readings. So we have to be able to correct for that. Equivalent airspeed. True airspeed is the actual speed of your airplane as it moves through undisturbed air. You can calculate your true airspeed from calibrated airspeed or equivalent airspeed using your E6B flight computer and taking pressure and temperature into account. Mach speed. Mach speed is the ratio of the aircraft's true airspeed in relation to the speed of sound. Your training aircraft will probably not have a Mach meter, but it's just something for informational purposes I've installed in the slide. Where your high performance aircraft have Mach meters. V speeds, velocity speeds, V speeds. There are certain color codes inside your airspeed indicator that we need to be familiar with. We have a white arc, we have a green arc, we have a yellow arc, and we have a red radial line. Now, at certain positions of the arcs in the instrument, they define certain things. So let's jump in. The bottom of the white arc, VSO, as you can see labeled there, bottom of the white arc, is the stalling speed or minimum steady flight speed in the landing configuration with the flaps and gear extended if you have retractable landing gear. If they're fixed and they're out, then your wheels are always going to be in landing configuration, not an issue. It's your in landing configuration when your flaps are extended at maximum landing weight is what this takes into account. Bottom of the white arc. Bottom of the green arc, stall speed, or we call VS1, or minimum steady flight speed in the specified configuration. This would be flaps up, gear up, or what we call the clean configuration. We're not dirty like VS1 or VSO. We're not dirty like him. The white arc. The white arc is the normal operating range for flaps. You should not be extending flaps outside of this speed regime or realm. Okay. Bottom of the white arc. We did that one already. Green arc, we talked about that. No, we didn't. Green arc is the normal operating range. Sorry about that, folks. Normal operating range. Airplane likes to be happy in green. You want to use caution in yellow, and red's dangerous. Top of the green arc is the maximum structural cruising speed. This is the maximum speed I want to fly in rough air. Don't want to be any faster than this because I don't want to cause any structural damage to the airplane. The yellow arc, smooth air operation range. We cannot be in this speed realm or regime unless we're in smooth air. So we definitely want to be there in turbulence. And then our red radial arc is the never exceed speed, VNE. Never NE, never exceed velocity. So think of the velocity as V, and you'd be okay. A couple things I want to talk about with the altimeter. The Colesman window. We adjust our pressure in the Colesman window, barometric pressure with a knob here. We talked about that, but we didn't talk about altitude, so we got to talk about indicated altitude. Indicated altitude is what you see on the altimeter, and it shows you your height above mean sea level. So we would be looking at this for indicated altitude, and it's telling us our height above sea level, which is actually a true altitude as well, our altitude above sea level, just looking at it. But pressure altitude is displayed when a Colesman window is set to 2992, like this one, where you're flying at a pressure altitude of 1,400 feet, roughly. That's all I really have to say about that. True altitude, your actual height above mean sea level. Absolute altitude, and we have that here, your absolute height above an object on the Earth's surface. There's a chart that we have to just give you standard international values, what the standard temperature should be. 1013, 14.7 pounds per square inch, what the atmosphere exerts itself at, 2992 inches of mercury. Not really much there, but what they want to get you to understand is this is what we would call a perfect atmosphere when we're determining aircraft performance and stuff like that. And the atmosphere is not always perfect. You have to keep that in mind. It is not always going to be 15 degrees Celsius at sea level. I don't think I've ever seen it. Talked about the vertical speed indicator. We're going to flow down, and we're going to talk about blockage. Now, in the case where our Pitot tube, we're back here at our Pitot tube, and again, our airspeed indicator is driven by the Pitot static system. So the Pitot tube's feeding it, and the static system's feeding it. That is the only instrument that takes both. Alright, if we block the ram air hole, but the drain hole is open, the airspeed's going to drop to 0. If we block the Pitot tube, the drain hole, we're not getting any ram air pressure inside the instrument, as we talked about before. But we will still get the static pressure. Now, what will happen in this case is the airspeed indicator will react like an altimeter. From the point where you blocked up at your drain hole and your ram air tube, if we increase the altitude from that point where we blocked up at, it's going to act like an altimeter. It's going to go high as we climb, and as we descend, it's going to show a lower reading. So we just want to focus that this is the only instrument that's going to be affected if we lose the ram air. If the static system is open, the altimeter and the vertical speed indicator will be fine. Sorry about that little interruption there. Alright, now, if the static port is blocked, as indicated here, the airspeed indicator will react to changing the airspeed, but you're going to get incorrect readings. The altimeter is going to pretty much stay where it's at, because the static port is iced over a block, and the VSI is not going to be any good to you. I'm sorry, we're almost through this, and then finally I want to talk about the gyroscopic system, the electrically operated gyros. Now, this is a turn and slip indicator. This turn and slip indicator is indicating a left turn and a skid. Alright. The gyro in here is vertical. And it just resists, it senses the yawing sources. Alright. There's a restraining spring in there, and we have an inclinometer there that tells us whether our turn is coordinated, and we'll go into detail with that. I actually have a pretty cool video to show you guys later. But the difference between the turn and slip indicator and the turn coordinator is that this gyro is actually canted or tilted. And in the turn coordinator we can sense rate of roll, rate of turn. But turn coordinators are more prevalent in training aircraft. And we're going to go into depth with that a little bit later. But that's basically at the private pilot level, that's the difference that we want to talk about. And we use this tool to establish standard rate turns. When you do your view limiting device flying with your instructor, you're going to be watching this thing. You're really going to be coordinating your turns with this, you know, visually. And, well, I'm getting really stuffy here. I'm going to cut it right here. Again, I'd like to thank you for watching. Again, I'm Kieno Thomas, your instructor. If you have any comments, questions, concerns, please email me at kienothomas@gmail.com. In the subject box, please put aviation, as I do lectures on other things in engineering and mathematics and other sciences. I'll know you exactly what your question is about in particular when I see aviation in the subject box. I thank you for your time. Thank you for watching. Be safe, and stay tuned for more videos. Thank you very much for watching.